Uh, Good afternoon. My name is Bong Kang, and I'm from KAI's Smart Sensor System Laboratory from Korea. Today, I will introduce about the silicon optical phase array we've designed. As the title suggests, I will talk about the design of phase shifters and the resulting power consumption and operation speed of the optical phase array. In addition, I will talk about the design of some radiator array structure that can steer the beam in the longitudinal direction without any wavelength tuning. So I'm going to make my presentation in this. Excuse me for a moment. So I'm going to make my presentation in this order. First, I'll give you some brief introduction about the LiDAR and optical phase array technology. And then I will discuss about some component devices like phase shifters and tunable grating radiators. And then I'll explain the integrated devices and the experimental results of that. So I think many of you are already may be familiar with the OPA and LiDAR, but I'll just briefly explain them before discussing our main topic. LiDAR is an abbreviation for the light detection and ranging, and it is technology being developed to replace some existing sensors such as LiDAR. While LiDAR uses some radio waves, LiDAR uses infrared waves. As LiDAR uses such infrared waves, the diffraction limit is reduced further. So even using a smaller sensor than the LiDAR, we can detect wider range and with some higher resolution. Because of this feature, LiDAR is attracting many attention. And there is many kinds of LiDAR, such as mechanically spinning LiDARs and flash LiDARs and optical phase array, etc. Among them, the optical phase array is getting the most attention because it can be developed by applying the silicon photonics technology. There are also many other advantages of optical phase array. You can make it in very small size, and very stable operation is possible than conventional LiDARs. And also mass production is easy as the technology becomes mature. So let's first look at the basic operating mechanism of OPA. Because it is a device that imitates the LiDAR, it works on the same principle, whereas the entire operation is done in the photonic integrated circuits made by the silicon photonics technology. So light is sent from the light source into the PIC chip and is split into several channels. The light split into the channels is given a specific phase for each channels through the phase shifters. The direction of the beam in the horizontal direction is determined by such phase condition. So we need to sophisticatedly care about the phase. And after passing the phase shifters, the light reaches the radiator. Although the radiators seems to be far away in this picture, actually they are very close together in an array structure. And this causes the light from each radiators to interfere and forming the beams at various angles. It is like the diffraction occurs in the double slit. So using the strongest beam among them, beam scanning is performed in the desired direction in the OPAs. So let's say that direction in which the radiator arrays are arranged as the horizontal direction, and the perpendicular direction is the longitudinal direction. So as I mentioned earlier, in order to steer the beam in horizontal direction, the appropriate phase set must be applied into the OPA via the phase shifters. Therefore, the steering speed and power consumption for the beam scanning are determined by the performance of the phase shifters. So many studies have developed various types of phase shifters. And many OPs have used their thermal optic phase shifters that can change the refractive index with the temperature change. Compared to the electro-optic method, which controls the concentration of carrier in the waveguide regime, the thermo-optic method does not change the insertion load due to the bias, and it enables some stable operation during phase change. However, the disadvantages are high power consumption and limited speed. On the other hand, the electro-optic method consumes less power and operates faster, but the insertion loss is large because the carrier must be present inside the waveguide region where the light passes. So, but although recent papers have addressed this breakthrough in innovation, a complex fabrication process or some techniques are required in those cases. Yeah. The phase shifter structure I've designed is like this. And it has a PIN junction structure on the center and controls the refractive index of the waveguide regime by the carrier injection mechanism. Detailed design specifications are like this, and the most important one is the I region width, which is the distance between the PN end of the regions, and it determines the performance of the phase shifter, so it is designed in several specifications. So before the fabrication, I've simulated the tuning efficiency and propagation loss of the phase shifter according to that I region is. The narrower the I region is, the more efficiently the carrier is injected into the waveguide, so which increases the tuning efficiency and enables phase control by the less power. However, the narrower the I region is, the greater the propagation loss occurs because the evanescent wave of the light passing through the waveguide is located in some heavily doped region, causing the propagation loss. So as you see, this propagation loss is dramatically reduced when it is over 1.5 micrometers. But however, in actual fabrication process, the loss could be much larger due to some factors such as fabrication error that made in some implantation or spreading or annealing stage. So it was turned to be to have best performance when it is designed with 2.5 micrometer. So the result of measured performance of phase shifter is like this. And as expected, the larger the I region is, the more power was consumed for the phase shifting. And the tuning efficiency was 1.7 milliwatt per pi phase shifting. In the case of the I region width was 2.5 micrometer. And at that case, the propagation loss was 3 dB, which is somewhat larger than the simulation result. And we guess that is from some fabrication errors I mentioned. And the operation speed was also measured, and we confirmed it as about 20 megahertz for the operation. It may seem to be quite slow because many electro-optic devices nowadays provide more than gigahertz operation speed, but this operation speed is still faster than the many circuits such as DAC, which is required for the actual use of OPA. So therefore, it does not limit the speed of the whole OPA system at this stage. Yeah, and let's talk about the longitudinal steering. The various methods are applied for the longitudinal beam steering, but in most cases, the wavelength tuning is used. This is since the grating radiator is used for OPA in most cases, and grating radiator changes the radiation angle depending on the wavelength of incident light. So many popular papers controls the wavelengths like almost up to 100 nanometer of incident light, and that cause some unstable performance and some degradation. First, most of all, since the component devices of OPA have some tendency toward wavelengths, the operation becomes very unstable according to the wavelength tuning. In addition, some tunable laser sources are very large and expensive. And if we want to integrate the laser source in the OPA chip, it requires very high technology and some know-how to do that. And moreover, it is more difficult to make some tunable laser source, fine tunable laser source, which is capable of coherent operation. And coherent operation, as you know, is recently used for ranging in wide area. So to overcome such problems, the device was designed to control the radiation angle of longitudinal direction by adjusting the refractive index of a grating radiator regime, not the wavelength of incident light. So detailed design parameters are shown in this page. As you can see in the FIB image, 25.4 nanometer deep grating radiator arrays were fabricated and designed to allow NIN heaters to operate the end dopings formed between the radiators. So experiments were conducted using several types of junctions, but we found out that NIN heaters shows the best characteristics. So as I explained earlier, biasing the NIN heater causes current flow in the radiator region. So the heat is generated in the resistive region, which is intrinsic, and which is the grating radiator region. So the temperature goes up as we bias this heater, and the thermal optic effect causes the refractive index change of the grating region, and also the change of the longitudinal radiation angle. So by integrating two such devices, the device with the following structure was fabricated. Two OPAs with 64 channels are arranged so that the light is applied to one OPA according to the operation of the optical switch. So just one of two OPAs is operated at one time. And the light passes through the PIN phase shifter array, so it gets some specific phase conditions. And it is radiated through the tunable radiator array in the center. So this is our experimental setup. It contains a Fourier lens system and a voltage control stage. And we made some wire bonding of our OPA chip to our customized PCB. So this is the result of the beamforming. This is the beamforming patterns of the OPA1 if we call one of two OPAs as OPA1. As you see, these are each single points of the OPA beam steering. And since the beam is small, I checked with some red dot on the beam point. Of course, beam steering is possible in all ranges between these points, but the beams of the last points are just summarized. As you can see, beam steering of plus minus 22.5 degrees was achieved in the horizontal direction, and 5 degrees steering was achieved in the longitudinal direction. So this is the beamforming pattern of OPA2. The same horizontal and longitudinal steering range is obtained, but the longitudinal radiation angle was the opposite to the OPA1. This is because they share the same tunable radiators, but the light is incidented in opposite direction, so they may have opposite angle from each OPA. As you may notice, both OPAs are designed to steer or plus minus 5 degrees with respect to the zero longitudinal angle. So when the tunable radiator array is not operated, when we give no bias, both OPAs emit the beams at an angle very close to the center. And if we operate such tunable radiators, the angle of radiation becomes changes about 5 degrees. So as the result, 2D beam steering of 45 degrees in horizontal direction and 10 degrees in the vertical direction, longitudinal direction was implemented using just monochromatic sources only. And this is some further analysis of operating characteristics of tunable radiator array. As you see, as a result of measuring the movement of the beam with respect to the applied power, it was confirmed that it is power moved quite linearly as the angle moved quite linearly as the power increased. And at this time, the tuning efficiency was about 0.9 degree per watt. We first proposed this tunable grating array structure with OPA with array factor of 1 times 16, but this time we increased it to 64 array factor, so more power was consumed for the steering, but we confirmed that it is quite scalable, so we can apply it to more bigger OPs. And it was also measured whether the beam of OPA is degraded by the operation of the such tunable radiator array. The graphs here show the beam patterns from the zero bias to bias for the maximum steering in longitudinal direction. And this is the characteristics of H beam according to the longitudinal steering range with the operation of tunable grating radiators. As you see, the longitudinal and transversal, which is horizontal, divergence angle remains quite same, and side lobe level also remains shows no significant change. So we can say it is confirmed that stable longitudinal direction, longitudinal steering using monochromatic source is possible. So in summary, 2x64 OP was designed using fabricated using designed phase shifters and tunable grating radiator. We achieved beam steering of 45 degrees horizontally and 10 degrees longitudinally. 450 resolvable points were obtained, and frame rate was about 2 kHz for the OPA. Such a radiation angle of the beam size, such a radiation range or the divergence of the beam can be easily be scaled by just adjusting the size or number of the OPAs. Yeah, thank you. Feel free to ask any question, please.